Hi students, in this video we are going to talk about the mathematical expectation of a random variable. It is the value that x can take on average when we perform an experiment a large number of times. We also call it an expected value of x. Okay? Before I give you definition, let me motivate you with an example. Say we have a box with 10 balls, 2 balls with a label 1, 3 balls with a label 2, 2 balls with a label 3, 3 balls with a label 4, 1 ball with a label 5. Here the random experiment is picking a ball at random. Let x denote the label of the selected ball. Label of selected ball. Here x is going to be discrete type random variable which take the values 1, 2, 3, 4, 5. If I ask you what is an average label that we can pick, it is going to be average of these 10 numbers. 1, 1, 2, 2, 2, 3, 3, 4, 4, 4, 5. How do you get average of these 10 numbers? Simply 1 plus 1 plus 2 plus 2 plus 2 plus 3 plus 3 plus 4 plus 4 plus 4 plus 5 by 10. If I group these 1s and these 2s and these 3s and these 4s and these 5, then we can write, if I separate the summation, 1 times 2 by 10 plus 2 times 3 by 10 plus 3 times 2 by 10 plus 4 times 3 by 10 plus 5 times 1 by 10. This 2 by 10 I can realize as the probability of x taking the value 1. That is probability of selecting a ball with a label 1. This 3 by 10 we can realize as probability of x taking the value 2. This 2 by 10 we can realize as probability of x taking the value 3. This 3 by 10 we can realize as probability of x taking the value 4. This 1 by 10 we can realize as probability of x taking the value 5. Okay? If Px is a PMF of x, then we can write the summation in terms of PMF like this. 1 times Px of 1 plus 2 times Px of 2 plus 3 times Px of 3 plus 4 times Px of 4 plus 5 times Px of 5. So this average label value we can see as weighted average of 1, 2, 3, 4, 5 with weights being corresponding PMF values. Okay, so this is the average label value that we can pick. Now we are going to see formal definition of mathematical expectation of a random variable. Okay, fine. First, let us see the definition in the case of discrete type random variable. Definition: let x be a discrete random variable with a PMF Px and support Sx, and if summation mod x p of x where x varying over Sx is finite, then we say expectation of x exists and defined as summation x into p of x where x varying over Sx. Okay, this looks fine, This is what expectation of x should be if it makes sense, as it is weighted average of x values over Sx with the weights being corresponding PMF values. Fine. Why we are demanding this? First of all, if the support Sx is finite, then this is going to be finite sum. Finite sum always finite. In that case, expectation of x exists. Fine. So this will be the expectation of x. But when Sx is countable infinite, this is going to be a series. Okay, that series is this. Summation x belongs to Sx. You can write like this: mod x px of x. It's okay whether you put modulus for PMF value or not, because PMF values are positive over Sx, right? So we can also write like this. Okay, that means we are demanding this. We want this to happen. That means we want this series to be absolutely convergent. What is the meaning of absolutely convergent? A series AN is said to be absolutely convergent if the series mod AN is convergent. Okay, if this is convergent, automatically this will convergent, but this convergent doesn't mean that this convergent. I will give an example here. If you look at the series summation n equal to 1 to infinity minus 1 to the power of n by n, this is the convergent series whose sum is log 2. Okay, but this is not convergent absolutely, because if you look at this one, okay, it's going to be harmonic series. We know that this will diverge to infinity. Okay, so okay, fine. What is the problem with convergent but not absolutely? They are called conditionally convergent series. Okay, the problem is the sum depends on the order of the summation. There is a famous theorem called Riemann rearrangement theorem, which says that if you take any conditionally convergent series, you can rearrange the terms to get any sum you want from minus infinity to infinity, including this minus infinity and infinity. Okay, that means for conditionally convergent series, the sum depends on order of the terms that we are using in the summation. Okay, that should not be the case in our definition. In whichever order we take x from Sx in the summation, we should end up with the same sum. That will be guaranteed only if this is absolutely convergent. Okay, that's why we are demanding this. Then only this summation is meaningful in our case. Okay, so fine. Okay, let me clear this. Next, let me give a analogous definition for continuous case. Let x be a continuous random variable with a PDF f of x, and if integral minus infinity to infinity mod x f of x dx is finite, then we say expectation of x exists and it is defined as integral minus infinity to infinity x f of x dx. Okay, we can actually write this integral as integral over Sx. The reason is outside Sx the PDF is 0. This also we can write integral over Sx. Okay. Now this looks analogous to the above definition. Only thing is summation replaced by integration, PMF replaced by PDF. Okay. So you should know one thing, that integration is continuous analogous of the summation. If you want to sum over some discrete set, you use the summation. If you want to sum over some interval, you use integration. Okay. So this is also, you can see as some weighted sum of x with the weights being f of x over Sx. Okay, fine. Okay, this makes sense. Again, here if Sx is bounded interval, this is going to be definite integral, this is going to be finite. In that case, expectation of x exists. When Sx is infinite interval, then as an improper integral, this should be absolutely convergent. Okay, then only we say expectation of x exists. and expectation of x is defined to be this one. Okay, fine. Now, so we have a notation for expectation of x. The expectation of x denoted by this e of x, we read it as expectation of x. Okay, this is a notation e of x, but we read it as expectation of x. Fine. Okay. Next, let's see some examples. Example, let x be a discrete random variable with a PMF P of x equal to 1 by 2 to the power of x for x equal to 1, 2, 3, so on, 0 otherwise. Okay, let us see if expectation of x exists for this distribution. Okay, fine. So, here the support of x we can see 1, 2, 3, so on. Okay, so to see if expectation of x exists, we need to look at this summation mod x p of x, where x varying over sx. Okay, as the support is countable infinite set, this is going to be infinite series. So we need to check if this series is convergent. Fine. Okay, let's look at this summation. Here I am using dummy variable n instead of x, as it will look good. Okay, summation mod n p of n where n over sx. Okay, here support of x consisting of only positive values, so we can replace mod n with a n, and the PMF value at n going to be what? 1 by 2 to the power of n. So in the next step we will write summation n times 1 by 2 to the power of n equal to 1 to infinity, which is simply the series summation n by 2 to the power of n for n equal to 1 to infinity. So we need to check if this series is convergent. We are going to use the ratio test. As this is series of positive terms, we can apply ratio test to see if it convergent. Here, if I take an equal to n by 2 to the power of n, okay, then let's look at limit of an plus 1 by an. Okay, if this limit is less than 1, then we can say it is convergent. If it is greater than 1, we can say it is divergent. If it is equal to 1, this test doesn't say anything. Okay, fine. Now here an equal to n by 2 to the power of n, which is positive. Now let us look at an plus 1 by an. So what is an? N by 2 to the power of n. So an plus 1 going to be n plus 1 by 2 to the power of n plus 1. An is n by 2 to the power of n. This gets simplified to n plus 1 by 2n. If I take n common, I can write 1 plus 1 by n 2. Okay. Now if I look at limit of this, so limit of an plus 1 by n going to be limit of this 1 plus 1 by n by 2. As n go to infinity, 1 by n go to 0. So this limit going to be 1 by 2, which is less than 1. Okay. Therefore, by ratio test, this series is convergent. Okay. Hence, we can say expectation of x exists. Now, expectation of x equal to summation n varying over sx n times p of n. Okay, so now let's compute expectation of x is what? Summation n equal to 1 to infinity as support of x consisting of numbers 1, 2, 3, so on. So expectation of x is summation n equal to 1 to infinity n times the PMF value at n is 1 by 2 to the power of n. So if I take 1 by 2 out, then we can see inside summation n equal to 1 to infinity n times 1 by 2 to the power of n minus 1. This look like summation n equal to 1 to infinity n times x to the power of n minus 1. Okay, for mod x less than 1, this is exactly expansion of 1 minus x whole to the power of minus 2. Okay, here x equal to 1 by 2. So this is going to be equal to what? Next step we will write 1 by 2 times this one, this expansion we can write as 1 minus 1 by 2 to the power of minus 2. Okay, this value will be simplified to 4. So half times 4 is equal to 2. So the reason is this. Okay, therefore expectation of x equal to 2. Fine. Okay, next example. Let x Example, let x be a discrete random variable with a support Sx consisting of 1, 2, 3, 4 and the PMF value at 1 equal to 4 by 10, at 2 equal to 1 by 10, at 3 equal to 3 by 10, at 4 equal to 2 by 10. Okay. Now here we want to find expectation of x if exists. Okay. So to see if it exists, we need to look at summation mod x p of x where x varying over sx. As sx is finite, this is going to be finite sum. Finite sum always finite, so expectation of x exists. So let's go ahead and compute expectation of x, which is going to be weighted average of x values over sx with weights being corresponding PMF values. So expectation of x equal to 1 times 4 by 10 plus 2 times 1 by 10 plus 3 times 3 by 10 plus 4 times 2 by 10, which is going to be simplified to 2.3. Therefore, expectation of x equal to 2.3. Okay, fine. Next example, let x be a continuous random variable with a PDF f of x equal to 4x cube for 0 less than x less than 1, 0 otherwise. Let us try to find expectation of x if exists. Okay. To see if expectation of x exists, we need to look at integral minus infinity to infinity mod x f of x dx. If this is finite, then expectation of x exists. Okay. So, but as you can see, the support of this x is interval 0 to 1. We simply have to integrate over 0 to 1 as PDF is 0 outside 0 to 1. So, mod x 4x cube dx. This is a definite integral, so it's going to be finite, so expectation of x exists. Now let's go ahead and compute expectation of x. Expectation of x is what? Integral minus infinity to infinity x f of x dx. As we can see, support of x is interval 0 to 1, so we simply have to integrate over 0 to 1 with a PDF 4x cube. So 0 to 1 x 4x cube dx. This is going to be 0 to 1, 4 is out, x to the power of 4 dx. Okay. Now integral of x to the power of 4 going to be x to the power of 5 by 5, 0 to 1. If you apply limits, it's going to be 1 by 5 minus 0. So 4 times 1 by 5, it's going to be 4 by 5. So therefore, expectation of x is going to be 4 by 5. Okay? Fine. Next, we can see the note. If the support of discrete random variable is finite, then we don't have to check for absolute convergence of this series, as this is going to be finite sum always finite. So expectation of x exists. Similarly, if the support of continuous random variable is bounded, then we don't have to check for absolute convergence for this integral, as this is going to be definite integral which is going to be finite again. So again expectation of x exists. Okay. So whenever we have a finite support in the case of discrete random variable, we can directly go ahead and compute expectation of x as it exists. Okay. And similarly, whenever we have a bounded interval as a support for continuous random variable, we can directly go ahead and compute expectation of x as expectation of x exists in this case also. Okay, fine. Next. Now let me give an example of a discrete type random variable for which expectation of x do not exist. Okay, here is an example. Let x be a discrete random variable with support sx consisting of values of this form minus 1 to the power of n plus 1, 3 power n by n for n equal to 1, 2, 3, so on, and PMF values at these points equal to 2 by 3 power n, that is px of minus 1 to the power of n plus 1 times 3 power n by n equal to 2 by 3 power n for n equal to 1, 2, 3, so on. Okay. As we can see, support of x is not finite. We need to check convergence of this series to see if expectation of x exists. Okay. Now, here the summation mod x px of x, where x varying over sx. So the points in sx are in this form. So we can write the summation like this. Summation n equal to 1 to infinity modulus of minus 1 to the power of n plus 1, 3 power n by n into PMF value of this, which is 2 by 3 power n. Okay, so next step we can write summation n equal to 1 to infinity. If I apply modulus here, so you'll end up with a 3 power n by n into 2 by 3 power n. 3 power n, 3 power n cancel. So if you get the 2 out, you will write summation n equal to 1 to infinity 1 by n. Okay, so we know that this is a harmonic series which is diverges to infinity. So expectation of x do not exist. But if you try to compute expectation of x directly, what is that? Expectation of x is summation x into px of x, where x varying over sx. In this case, you will write like this: summation n equal to 1 to infinity minus 1 to the power of n plus 1 into 3 power n by n into 2 by 3 power n. This 3 power n, 3 power n cancel. If you get the 2 out, you will end up with the 2 times n equal to 1 to infinity minus 1 to the power of n plus 1 by n. Okay. Now, this is actually convergent series by Leibniz test, which is actually conditionally convergent series, and sum equal to log 2. So it's going to be 2 log 2. Okay, but this doesn't mean that expectation of x exists. Okay, that's why whenever we have a infinite support in the case of discrete type random variable, first we need to check convergence of this series before we go ahead and compute expectation of x. Okay, fine. Okay, now let me give an example of a continuous type random variable for which expectation do not exist. Here is an example. X be a continuous random variable with a PD of f of x equal to 1 by pi 1 by 1 plus x square for minus infinity less than x less than infinity. Here support of x we can see infinite interval minus infinity to infinity, which is not bounded interval. So we can't be sure about existence of expectation x. So we need to look at this integral minus infinity to infinity mod x f of x dx. Okay, we need to see if it is finite. Then only we should go for finding expectation of x. Okay, now this is what integral minus infinity to infinity mod x. What is f of x? 1 by pi 1 by 1 plus x square dx. So if I write 1 by pi out, integral minus infinity to infinity mod x by 1 plus x square dx. Now this integrand is even function, so we can write this integral as 2 times integral 0 to infinity. So in the range 0 to infinity, mod x same as x, so we can simply write x by 1 plus x square dx. So this improper integral we can write 1 by pi limit t tends to infinity The 2 if I write inside 0 to t 2x by 1 plus x squared dx. Now the 2x is derivative of 1 plus x square, so the integrand look like f dash x by f of x. So integral of 2x by 1 plus x square going to be log 1 plus x square. So it's going to be 1 by pi limit t tends to infinity log 1 plus x square if you apply the limits 0 to t. Okay, now fine, let's do. So this is going to be, after applying the limits, 1 by pi limit 1 plus t square minus log 1. Log 1 is 0. Now as t go to infinity, 1 plus t square also go to infinity. That implies log 1 plus t square also go to infinity, because log x is unbounded function, increasing function. So log 1 plus t square also go to infinity. So the integral is diverges to infinity. So expectation of x do not exist. Okay, but if you try to compute directly without checking this absolute convergence, okay, if you look at this integral minus infinity to infinity x f of x, okay, as expectation of x, if then what happen here, see. So integral, I can write 1 by pi out. So x by 1 plus x squared dx. Now this you might want to see as limit a tends to infinity minus a to a x by 1 plus x squared dx. But this time this integrand is going to be odd function. Odd function means a function f is said to be odd function if f of minus x equal to minus f of x. Even function means f of minus x equal to f of x. Okay, for odd function this integral is going to be 0. So you have now 1 by pi limit a tends to infinity 0. So limit of 0 going to be 0, so which is fine. Okay, so you might want to say expectation of x 0, but that is not the case. Here expectation of x do not exist. Okay, after checking only absolute convergence of this integral, then we should look at expectation of x. Then only we will say expectation of x exists. Okay, fine. Now let me clear this. Now let's see what should be expectation of indicator random variable. Okay, that omega script of p be a probability space and a be an event in event space, then expectation of ia equal to probability of a. Ia is indicator random variable of event a. Ia defined like this. Ia take the value 1 if a happens, that means outcome sitting in a. Otherwise take the value 0. Okay, so ia is a random variable which takes only two values 0 and 1, that is support of ia is finite. So expectation of ia exists and that can be computed like this. Expectation of ia going to be weighted average of this 1 and 0 with the weights being their corresponding probabilities like this. 1 times probability of ia equal to 1, 0 times probability of ia equal to 0. So this is going to be equal to probability of ia equal to 1. Ia take the value 1 if and only if a happens. So this will be exactly equal to probability of a. Okay. So therefore expectation of indicator random variable a going to be exactly probability of an event a. Okay. Fine. Next. Now expectation of a function of a random variable. If you are given a random variable x with its probability distribution and y equal to g of x, then you want to find out expectation of y if it exists. Okay, how do we do that? One obvious approach is first you find probability distribution of y in terms of probability distribution of x. That is, if x is a discrete random variable, you may be given PMF of x, then you want to find PMF of y in terms of PMF of x. Okay, we know how to find the PMF of y in terms of PMF of x. Okay, we have seen probability distributions of functions of random variables. Okay, if x is a continuous type random variable, then you may be given PDF of x, then you want to find out PDF of y in terms of PDF of x. You know how to do that. Once you get hold of this probability distribution of y, then you can look at expectation of y like this. Expectation of y is going to be this summation provided it converges absolutely when y is discrete type random variable. If y is continuous type random variable, we are going to see expectation of y as integral minus infinity to infinity y fi of y, provided this integral converges absolutely. Okay, so this is how one can find out expectation of y. This is one approach. Let's do one problem using this approach. Okay, fine. Example. Let x be a discrete random variable with a support Sx equal to -101 and the PMF values at -101 are this. Px of -1 equal to 0.2, Px of 0 equal to 0.5 and Px of 1 equal to 0.3. And y equal to x square, that is g of x equal to what? X square. Now we want to find out expectation of y. Okay. Our idea is to first find PMF of y. Here PMF of x is given. First we have to find PMF of y. Then we can look for expectation of y. Okay. And how do you find the PMF of y? We have a connection between PMF of y and PMF of x. That is, here first of all, support of y is going to be 0 and 1. Okay. So the mapping from Sx to Sy -1, 0 and 1. Here y take the value 0 and 1. -1 and 1 map to 1. 0 map to 0. Okay. So, and Py of y for y belongs to Sy is what? Px of G inverse singleton y. Okay. So this is the connection between PMF of y and PMF of x. Okay. Now let's try to find out PMF of y values for 0 and 1. Okay. First of all, Py of 0 going to be same as Px of 0. The reason is, so what is the Py of 0? It should be Px of G inverse of singleton 0. But inverse image of 0 is only 0, so it should be Px of 0. That's why Py of 0 same as Px of 0, which is 0.5. Similarly, Py of 1 going to be Px of -1 plus Px of 1. The reason is Py of 1 should be Px of G inverse of the singleton 1. But under this function, what is the function? X square, right? G function. So here -1 and 1 both go to 1. -1 go to -1 square, which is 1. 1 go to 1 square, which is also 1. So the inverse image of 1 going to be under this function -1 and 1. So this is going to be Px of -1 plus Px of 1. Okay. Fine. So that's why the Px of -1 value 0.2. Okay. And Px of 1 value 0.3. So 0.2 plus 0.3. So Py of 1 equal to 0.5. So we got hold of PMF of y. Now we will find expectation of y. Here support of y is finite. So expectation of y will exist. Now let us try to find out expectation of y directly. So expectation of y is going to be what? Weighted average of these y values with the weights being corresponding PMF values like this. 0 times Py of 0 plus 1 times Py of 1, which is 0 times 0.5 plus 1 times 0.5, which is 0.5. Okay. Hence expectation of x square going to be 0.5. Okay. This is a one approach to find the expectation of y. Okay, fine. Now, question is, do we really need to struggle to find out probability distribution of y to find out expectation of y? Can we somehow get through this problem without finding probability distribution of y? Answer is yes. Actually, we don't need to find out probability distribution of y to see if expectation of y exists. Even if you want to find out expectation of y, we don't actually need probability distribution of y. We can work out just using probability distribution of x. Okay, let's have a close look at this problem here. Here, expectation of y, we got like this: 0 times 0.5 plus 1 times 0.5. Here 0 weight is 0.5, 1 weight also 0.5. Let's break down this one like this: 0 times 0.5. This 1 times 0.5, let's write like this: 1 times 0.2 plus 1 times 0.3. Okay, this 0 I'm going to realize as 0 square. This 1, because minus 1 weight is 0.2, let me realize as minus 1 whole square times 0.2. This 1, let me realize as 1 square, as 1 weight is 0.3. 1 square 0.3. Now this look like g of 0 times px of 0, g of minus 1 times px of minus 1 plus g of 1 times px of 1. So that means this look like this: summation x belongs to sx, summation varying over sx, as 0 minus 1 1, g of x times px of x. That means we are looking expectation of y as weighted average of g of x values with weights being corresponding PMF values of x, where x varying over sx. Okay, because g of x take the value g of x when x take the value x. Okay, so g of x weight should be same as x weight, but thing is, here this g of x values may be repeated. Here you see g of minus 1, g of 1 are same, but they are given different weights. Once we are given weight of minus 1, once we are given weight of 1. Okay, so here summation varying over sx. Okay, so fine. So we are looking at expectation of y, that is expectation of g of x. Okay, this is expectation of g of x as a weighted average of this g of x values with the weights being corresponding PMF values of x. Okay, where x varying over sx. Okay, let's do the same problem with this approach. Obviously we get the same answer. So summation of x square px of x, where x varying over sx. Here g of x is x square. Okay, that is weighted average of this g of x values with the weights being corresponding PMF values of x, where x varying over sx, which is going to be minus 1 square times px of minus 1 plus 0 square times px of 0 plus 1 square times px of 1. The whole thing sum up to 0.5, same thing. Okay, so here also we end up with the same thing. So we don't have to find out probability distribution of y to find out expectation of y. Next we are going to see a theorem about this result. Okay, fine. Next theorem, there are two statements. I am going to read one by one. Let x be a random variable and y equal to g of x. If x is a discrete random variable with the PMF p of x and the summation mod g of x p of x, where x varying over sx is finite, then expectation of y exists, and that expectation of y is simply going to be a weighted average of this g of x values over this Sx with weights being corresponding PMF values of x. That is, expectation of y is summation g of x p of x where x varying over Sx. This is going to be expectation of y. Similarly, in a continuous case, statement is this. If x is a continuous random variable with a PDF f of x and the integral minus infinity to infinity mod g of x f of x dx is finite, then expectation of y exists, and that expectation of y equal to integral minus infinity to infinity g of x f of x dx. This is how we can compute expectation of y without actually finding probability distribution of y. Okay, fine. Proof. It is given that summation of mod g of x p of x where x varying over Sx is finite. First we need to show expectation of y exists. For that we need to show summation mod y py of y where y varying over Sy is finite. Okay, we are going to show this summation exactly equal to this summation. Since this is finite, this must be finite. That's how we are going to show expectation of y exists. Okay, then we will show that expectation of y equal to this by showing that this summation exactly equal to summation of y py of y where y varying over S5. Okay, this is how we are going to prove this theorem. Fine. Okay. First of all, we have a mapping G from Sx to Sy. Okay. Let's say Sy consisting of y1, y2, y3 and so on. So my idea is to break this whole Sx into groups. One group is inverse image of y1, another group is inverse image of y2, another group is inverse image of y3 and so on. Okay, here this summation varying over Sx, right? So let's sum over these groups like this. Okay, so let me consider this summation varying over Sx. So first of all, let me sum over each group. Okay, first for each y, first I sum over this group, then I go to the next y, then I sum over this group and so on. That's why we got a double summation here. Summation y belongs to Sy for this y, this summation varying over x such that g of x equal to y means what is this? X belongs to g inverse of this singleton y. Okay, so this summation varying over inverse image of y. For each y, we have a group that is g inverse of singleton y. So we are running over that group. Okay, so that's why this single summation we are writing as this double summation. Okay, now in this summation, in this inner summation, g of x equal to y, right? So this is going to be mod y. This mod y is common to every term in this inner summation, so it can come out of the summation. Okay, then we can write like this. Okay, first of all, this g of x replaced with y, so it's going to be double summation y belongs to Sy. The inner summation is summation x varying over this g of x equal to y mod y into pxy. Now you can take this mod y out, which is okay. Now you can take this mod y out of the inner summation, so it's going to be like this. Now this is precisely px of g inverse of y. Okay, the probability of, see this, we are adding PMF values over x belongs to what? G inverse y. That is, this is exactly px of g inverse y. So this is exactly what? Py of y. So we have summation mod y, py of y. So in the next step, we can write So this whole thing I can replace with Px g inverse y, which is exactly we mean by Py of y. So this left hand side exactly equal to this right hand side, which is summation of y belongs to S5 mod y Py of y. Okay. Since this is finite, it is given that this is finite, so this must be finite. Therefore, expectation of y exists. Okay. In similar fashion, next we are going to show expectation of y equal to this. Okay. Let me clear this. Next, now my goal is to show this exactly expectation of y. For that, I want to show this equal to summation of y Py of y, where y varying over S5. So in a similar fashion, if you break this summation into double summation, you see exactly everything looks same. Y will come out. So again, you end up with this summation. So this summation will be exactly equal to this summation of y Py of y, where y varying over S5. So which is exactly we mean by expectation of y when it exists, right? So therefore, this is going to be our expectation of y. Okay, this is how we compute expectation of y, where y equal to g of x, which is what summation of g of x px of x, where x varying over sx. Here we don't have to find out probability distribution of y. That is, we don't have to find out PMF of y to find out expectation of y. In practice, it is very useful result. Okay, fine. Next, note, it's very clear that if g of x is non-negative, then expectation of g of x also going to be non-negative. Because in the discrete case, what is the expectation of g of x when it exists? X varying over sx, g of x, p of x. And anyway, we know the PMF values are positive over Sx. Now you are saying that g of x is non-negative, so this term going to be non-negative. So sum of the non-negative terms will be again non-negative. In continuous case, what is the expectation of g of x when it exists? Which is integral minus infinity to infinity g of x f of x dx. We know that PDF always non-negative function. Now you are saying that g also non-negative, so this integrand going to be non-negative. So this integral also going to be non-negative as it represents area. So area will be non-negative quantity. So whenever g of x non-negative, expectation of g of x also going to be non-negative. Fine. Next, we can also see that expectation of x exists if and only if expectation of mod x exists. Okay, here g of x is mod x. Okay, as a function of a random variable. Okay, so expectation of x exists if and only if expectation of mod x exists. Okay, you can easily see from the definition of expectation. Fine. Let me clear this. Next. Okay, theorem. Let g1 of x, g2 of x are two functions of random variable x. Suppose expectation of g1x, expectation of g2x both exist. Then for any constants k1, k2, expectation of k1 g1x plus k2 g2x also exists. Not only that, expectation of this linear combination is going to be linear combination of this expectation. That is, expectation of k1 g1x plus k2 g2x going to be k1 times expectation g1x plus k2 times expectation g2x. Okay. Again, we are going to prove this theorem in discrete case only. Okay. Proof. Let's assume that x be a discrete random variable which support Sx and the PMF Px. Okay. First, we are going to show that expectation of k1 g1x plus k2 g2x exists. For that, we need to show the summation modulus of k1 g1x plus k2 g2x p of x, where x varying over sx. We need to show this summation is finite. Okay. Here it is given that expectation of g1x exists and expectation of g2x exists. That means we have these two things. Since expectation of g1x exists, we have a summation mod g1x p of x where x varying over sx is finite. Since expectation of g2x exists, we also have summation mod g2x p of x where x varying over sx is finite. Okay. Now, using this information, somehow we need to realize that this summation is finite. Okay. So, let us start with the summation and try to realize the sum is finite. Okay. So, let's do that. Here we are starting with summation mod k1 g1x plus k2 g2x p of x where x varying over sx. We are going to realize this is finite. Okay. We should know one inequality, something called triangle inequality, that is mod a plus b will be always less than or equal to mod a plus mod b. Okay, so that's why here mod k1 g1x plus k2 g2x will be less than or equal to mod k1 g1x plus mod k2 g2x. Okay, so again mod k1 g1x we can write mod k1 into mod g1x, mod k2 g2x we can write mod k2 into mod g2x. So so this will be less than or equal to this thing. Now if you separate the summation into two parts, it will be like this. You can take the mod k1 out like this, here mod k2 out. Then now we know that this is finite, right? This is also finite. So the right hand side, this is finite, so the whole thing is finite, as left hand side is less than or equal to this finite, so this must be finite. Therefore, we have this. Hence, we can say expectation of k1 g1x plus k2 g2x exists. Okay, let me clear this. Hence, expectation of k1 g1x plus k2 g2x exists. Now we need to show that expectation of k1 g1x plus k2 g2x actually equal to k1 times expectation g1x plus k2 times expectation of g2x. Okay. First of all, we know what is the meaning of expectation of k1 g1x plus k2 g2x when it exists. We can think the whole thing like a g of x. So how do we write expectation of g of x? Expectation of g of x when it exists, we write like this: summation g of x p of x where x varying over sx. Okay. Similarly, we can write expectation of k1 g1x plus k2 g2x like this. Okay. Summation of k1 g1x plus k2 g2x p of x. Okay. Now, if we separate the summation into two parts, we can write like this: k1 times this summation, k2 times this summation. This summation exactly expectation of g1x, this summation exactly expectation of g2x. Therefore, expectation of k1 g1x plus k2 g2x equal to k1 times expectation g1x plus k2 times expectation g2x. This is the result. Okay, let me clear it. Now corollary, expectation of ax plus b going to be a times expectation of x plus b. It follows from above theorem. Simply take k1 equal to a, g1 of x equal to x, k2 equal to b, g2 of x equal to 1. That is expectation of ax plus b times 1. So from above theorem it should be a times expectation of x plus b times expectation of 1. Okay, here expectation of 1, thinking 1 as like a g of x, it should be what? Summation of 1 times px of x, where x run over sx, simply going to be summation of PMF values over Sx. So by PMF property, we know that the total PMF values add up to 1. Okay, so that's why expectation of 1 going to be 1. So A times expectation of x plus b. Okay, further expectation of ax going to be A times expectation of x, simply taking b equal 0 in this corollary. Similarly, expectation of b going to be b, simply taking a equal to 0 in the above corollary. Okay, just keep in mind these results. Okay, fine. Let me clear this. Next, general theorem. Let's generalize it. Let g1, g2, so on, gn x are n functions of random variable x. Suppose expectation of gix exists for all I equal to 1 to n. Then for any constants k1, k2, kn, expectation of this linear combination, that is expectation of summation I equal to 1 to n ki gix also exists. Not only that, expectation of summation I equal to 1 to n ki gix going to be summation I equal to 1 to n ki times expectation of gix. This is the general result. In the above theorem, we proved for n equal to, that's our base case. Now we can use induction to prove this. Okay, so the proof by induction, so it's easy. Okay, so fine. Expectation of the linear combination is going to be linear combination of expectations. Okay, fine. Okay, let me clear it. Next. Okay, let's do an example here. Let x be a continuous random variable with a PDF f of x equal to 2 times 1 minus x for 0 less than x less than 1, 0 otherwise. Let's find the expectation of x square and expectation of 6x plus 3x square. All these expectations are going to exist here because our support is bounded interval. So we don't have to worry about existence of these expectations. Let's simply go ahead and find them. Okay. First, let's look at expectation of x. By definition, which is what? Integral minus infinity to infinity x f of x dx. Outside 0, 1, our PDF going to be 0. So we simply have to integrate from 0 to 1. So it's going to be 0 to 1 x times 2 times 1 minus x. So this is our PDF. Okay. So if you take 2 out, so integral of 0 to 1 x minus x square dx. So this integral going to be x square by 2 minus x cube by 3, limits 0 to 1. So it's going to be 2 times 1 by 2 minus 1 by 3 minus 0 minus 0. Okay, this is going to be 2 times 1 by 6. It's going to be 1 by 3. Therefore, expectation of x we got 1 by 3. Similarly, expectation of x square. Now you think like this is g of x. We know how to deal with the expectation of g of x. So this is going to be what? Integral minus infinity to infinity x square f of x dx. This is our g of x. Okay. So again, outside 0, 1, our PDF going to be 0. Simply we have to integrate over 0, 1. So integral 0 to 1 x square. This is our PDF. So if you take a 2 out, so integral 0 to 1 x square minus x cube dx. Again, this integral going to be x cube by 3 minus x to the power of 4 by 4, 0 to 1. So it's going to be 2 times 1 by 3 minus 1 by 4 minus 0 minus 0. Okay, it's going to be 2 times 1 by 12 It's going to be 1 by 6. So we got expectation x square equal to 1 by 6. Now expectation of 6x plus 3x square. One way is to do this again from scratch, like thinking this is like a g of x. Again, looking at integral of 6x plus 3x square into the PDF like this. We could have done like this, but since we already got expectation x square, actually this look like, let me clear this. This expectation of 6x plus 3x square look like expectation of some k1 g1x plus k2 g2x. So we have a theorem that says that this should be 6 times expectation x plus 3 times expectation x square. Since we already got expectation of x square, we can make use this result so that we can say it's going to be 6 times expectation x plus 3 times expectation x square, which is 6 times 1 by 3 plus 3 times 1 by 6, which is going to be simplified to 5 by 2. So this is how we can make use of the above theorem, okay, to answer this question. Expectation of 6x plus 3x square. Fine? Okay. Okay, let me clear this. Next. Okay, example. Let a horizontal line segment of length 5 is divided into two parts at random. If x denotes the length of the left hand part, then the reasonable PDF of x is f of x equal to 1 by 5 for 0 less than x less than 5, 0 otherwise. Okay, let's say this is a line segment of length 5 which is divided into two parts at random. Let's say we break here, then length of the left hand part is denoted by the random variable x. Here x can take any value in interval 0 to 5. Okay. Question is why this is reasonable PDF here. We know that this PDF value f of x actually measure of likelihood of x being near value x. Okay, that should be same in this case because we are breaking it random. So this PDF must be first of all constant. Okay, and we know that this x can take any value from 0 to 5 the length, so 0 otherwise. First of all, at least we can feel this. Now for c equal to 1 by 5 only, this will be a valid PDF. That's why this is going to be reasonable PDF in this case. Okay. Now let's try to find out expectation of x. Expectation of x by definition, here support is boundary interval, so we don't have to worry about existence of these expectations. We can directly find them. Expectation of x integral minus infinity to infinity x f of x dx. Outside 0 to 5, our PDF is 0, so we simply have to integrate from 0 to 5 x, and the PDF is 1 by 5, so integral going to be 1 by 5 x square by 2, 0 to 5, okay, 1 by 5, 25 by 2 minus 0, which is going to be 5 by 2. Okay, therefore expectation of x is 5 by 2. Then next we can see that expectation of 5 minus x, that is length of the right hand side part, okay, is going to be what? 5 minus expectation of x. The reason is we know that expectation of ax plus b going to be a times expectation x plus b. According to that, I can write 5 minus expectation x, and expectation of x we already got 5 by 2, which is 5 minus 5 by 2, again 5 by 2. Okay, fine. Okay, now let's look at expectation of x into 5 minus x. Okay, Similarly, integral from minus infinity to infinity. Now this is like a g of x, right? Okay. Integral minus infinity to infinity x into 5 minus x f of x. Here f of x is 1 by 5 in the interval 0 to 5, outside 0. So we simply have to integrate from 0 to 5 x into 5 minus x, and the PDF is 1 by 5. If I integrate this 1 by 5, 5x square by 2 minus x cube by 3, 0 to 5. So 1 by 5, 5 times 5 square minus 5 cube by 2 by 3. Again, if I take off 1 5 common, I will get 25 by 2 minus 25 by 3, which is going to be 25 by 6. Okay. Expectation of x into 5 minus x going to be 25 by 6. Now we can see that expectation of x into 5 minus x, which is 25 by 6, which is not equal to 5 by 2 into 5 by 2, which is expectation of x into expectation of 5 minus x. Here in general, if you think x is like a g1x, 5 minus x is like a g2x, then expectation of g1x into g2x may not be same as expectation of g1x into expectation of g2x. Okay, so in general we don't have this. Okay, we have expectation of g1x plus g2x. We can write expectation of g1x plus expectation of g2x, but for the product we don't have that. Okay, so hence in general expectation of g1x into g2x may not be same as expectation of g1x into expectation of g2x. Okay, fine. Okay, I think I'll stop now. Thank you.